In this video, we'll begin our discussion of section 12.4, velocity and acceleration. There really isn't much more here from what you learned about this in Calc 1 with derivatives. If I have a vector function that represents some positions on a space curve, right, that's going through space, and I want to find the velocity at a certain time, all I got to do is take the first derivative like we would have in Calc 1. We can do the same thing with acceleration, taking the second derivative. Now, the only thing that's a bit new here is the speed idea. This makes sense if we think about it. We talked about in Calc 1, remember that velocity, we take velocity and that was a direction and a direction and a magnitude, while speed just had the magnitude side of it. So we would take the absolute value, just get rid of the negative if there was a negative telling us a direction. Now, that doesn't make sense with a vector. I mean, I guess we could take the negative of it, but that would just shoot us in another direction instead of like just giving us a magnitude. Well, if we're just wanting a direction like negative 65 miles per hour going down or something, but I was just talking about like reading it, maybe I could go down into the earth with my car somehow, going negative 65 miles per hour somehow, but I look at my speedometer, it still says 65. That's the idea, right? That we just want the magnitude. I just want to know how fast I'm going. I don't really care about the direction, so I would take the magnitude. All right, so we're going to do a few examples. This is probably the shortest section out of chapter 12, which is only 5 sections. But I feel like this one is the most straightforward, so it will be the shortest one, probably the quickest for you. So if I wanted the velocity, if I want that vector, right, that is just the first derivative. So I take the first derivative of the function that I have, I get 2t, 1, 4t cubed. All right, that gives me velocity. If I wanted acceleration, I just take the derivative of that, which is my second derivative of the position function. So I get 2, 0, 12t squared. That's great. Okay, so acceleration velocity. If I wanted speed is the magnitude of velocity. So I'm just going to take the magnitude of that velocity up there. I get 4t squared plus 1 plus 16t to the sixth. But they actually said at 1, so we could have done a couple things. I did all that work to get formulas. I could have plugged it into my formula for all that. We have to do that for our velocity and our acceleration. So like now I had velocity of 1. I would just plug 1 into everything. I had to find the formula for that. For acceleration, I had to find the derivative so I could plug the 1 in. There was no other way around that. So plugging this in, I get 2, 0, and then I get 12. That's just plugging in. Now, taking this speed, because I just want the velocity of that thing, right now I made a formula, which is great, but I always feel weird with formulas like that. I just don't feel confident. I don't know why I don't. So instead, what we could do is I could just plug in this 1 here, and I just want the magnitude of that. Then I don't have to go through that whole formula. I just have to do the magnitude of the vector up there at 1. And that will give me an answer of square root of 21, and I'm done. I didn't have to do the formula and plug it in. Now, if I use the formula, I probably still got square root of 21, but I'm just trying to save you some work, because you have to find this anyway, so you might as well just find the magnitude of that one instead. Now, velocity and acceleration have to take the derivatives to get to the answer. You can't plug in 1 to velocity and take the derivative, because you would just get zeros, right? Because if you plug in 1, you're going to get all constants. If I take derivative of constants, I get zeros. It doesn't make sense in that context, but I can plug it in and get the speed. All right, let's take a look at another example. Velocity, acceleration, and speed, the same thing. So velocity here is going to be our first derivative. All right. Sometimes I would, if you're taking derivatives, like I said, if they get too complicated, then maybe do each by component. Well, I got negative t to the, for me, I need to see this as a 1/2. All right, this is negative 1/2 t to the negative 1/2. So this is going to be negative 1 over 2 to the square root of t. I'm going to leave that up there because we're going to take a derivative again in a moment. Derivative of t is 1. Derivative of e to the 3t is 3e to the 3t. Now we wanted to find acceleration. So I'm going to use this up here. It's easier. Negative comes down. I get a 1/4 t to the negative 3 over 2. So I get, now for this one, there's no negative, but I get 1 over 4 t to the 3 over 2. I can make positive since it went back to the bottom. Derivative of 1 is 0. Derivative of that one, it's another chain rule. So I get another factor of 3. All right, they didn't give us a t. So this one we can't plug in v to do a speed. So we're going to do the magnitude of velocity, which will be our speed. Now we get the square root of, right, if I square that first component, I get 1/4 t. Plus, I square 1, I get 1. And if I square that, I get 9e to the 6t. There's my magnitude. You just square each one. You don't need to. You could go and try to get like terms. Some professors want you to do that. I'm good stopping right there. I can see exactly what it's going to be. You're going to have to do some stuff with all this here in a moment, taking magnitudes and plugging them in elsewhere. There it will decide how things cancel out. In this kind of moment, that's not going to look better with a one fraction or not. It already doesn't. It's going to look worse than it does now. All right, let's try this example. Given now, we're going to work our way backward. This is what we called earlier an IVP. So given acceleration and some initial conditions, find position function. So we're working backwards now. I have AT, and now this is going to require integration. VT, if I want VT, it is the integral of AT dt. So we need to switch back to IJK form. The integrals, I wouldn't be too upset if you threw a component form in there. I just don't ever see it. I need to take a glance at our textbook and see if I can ever find it, if they put a component form inside of an integral. If you do it, not going to be upset. I just am not convinced that it's a common thing. So integral of e to the t is e to the t. Then we get negative e to the negative t, that's j. And then k, we'll get a t, because it was a 1. Okay, now we get to put a plus c. So we get to run through our initial condition. Now here we have this velocity of 0. I plug that into my function. I get 1i, minus j, 1j. Plugging 0, I get 0k. I still like to put it here. Plus c. And then now I set it to that initial condition up there that they gave to us. We solve for c by making the things on the left go to the right. If I minus the i's, they're gone. If I add that j, I get a 3j. So that is my c. So v of t is equal to, and I just had to add that into the j, e to the t I. And then I'm going to do 1 or plus, and then I'm going to put that 3 up front so I can use that subtraction. I think it just looks cleaner, easier to write. I make less mistakes when I do that. And then I got tk. We want plus 2, we just figured out c. All right, that's velocity. They want us to get all the way down to the position function r. If I want to find r and I have v, r of t is equal to the integral of v of t dt. So I'm going to plug all that in. E to the t I plus 3 minus e to the negative t j plus t k dt. All right. Taking my integration here, we have e to the t. We have I. We should leave that I. Mess that up. And then we have two parts here. I'm going to have 3t, and then I'm going to get plus e to the negative t. If I do that, think of going backwards. That's how I always figure these out. J plus 1/2 t squared k plus c. right? So r of 0, I get I, plus, if I plug a 0 in there, I get j, plus 0k, plus c, and then the initial condition they gave us was 3i j 2k, 3i j 2k. And I'm solving now by subtracting things over. We get c equals 2i. I subtract j, it's gone. The 2k is still there. So that's what c is. So now I have my final answer. R of t, I'm adding a 2 into the I. So I get e to the t plus 2i plus 3 to the t, 3t, not 3 to the t, plus e to the negative t, j. And then plus now we finally have something for k. 1/2 t squared plus 2. Okay, there is my original position function. So this shouldn't feel, I think you do IVPs like this in Calc 1 and 2, once you get to the integration part, I think is where you would do it, integration to get the plus C's, depending how ambitious your Calc 1 teacher was, if you got into it or not. But this idea shouldn't feel too disfamiliar to you. And then, like I said, going forward in DE, all we do are solve these problems called IVPs. Okay, I have one more page for you. This is going to feel like out of nowhere information, and it's because it's just in our book, and maybe it's going to be helpful for somebody, but I'm going to give it to you because I don't want it to be a disservice. This is another way to write acceleration. I have yet to really use this thing. What we're going to do is we're going to call this like V here that has no arrow over it. That's going to be our speed. So it'll be the magnitude of our velocity. What they call this is we can write acceleration like this if I have all those parts. It just feels a little overcomplicated. It is true, we can do that. I'm not going to prove that to you. This part that is v prime, that's the derivative of the speed. I'll give you this name, tangential component of acceleration. And then the kv prime, or kv squared part, that coefficient of that n thing there. I know this is a unit tangent vector. This n thing will be something we talk about in the next section, or yeah. So that is something related to the normal. We've heard the word normal before. This is component, normal component of acceleration. I'm going to show you that V, something with that that's going to get us to probably, it's a little useful if you have polynomials. I have another formula I'm about to give you that's going to have something to do with that. Right, so V is the speed. So it's the magnitude of the vector V, or the magnitude of R prime of t. Right? If I take the derivative of each side, I got v prime equals the derivative d dt of the integral of r prime of t, not the integral, but sorry, the magnitude. So here we can just get rid of that parentheses. The derivative of that. If I take that original equation that was up there and I square both sides, I have that. Okay, so we have those two things. We can replace certain things with that other equation with what's on the screen with definitions. And I'll show you how that's going to work out. Again, this is going to it feels out of nowhere, and it's kind of like, okay. They throw it in every calc book. Maybe one day I will see there's no derivative there. R dotted with R double prime integral, or sorry, I keep calling that, I don't know why I did that above, but the magnitude of R prime times the tangential or the unit tangent vector plus, and then the normal component of acceleration will become the magnitude of r prime crossed with r double prime magnitude divided by magnitude of r prime times n. So what we did is we placed certain aspects, solving parts of that equation. It's a bit confusing. Like I said, I see this in some books. I felt like a disservice just leaving it off completely. So we will leave it at that. I'm not going to ask a test question over this or anything like that. If anybody ends up using this in some of their applications in other classes, I would love to know in the future. If you ever want to email about it, please do so. I have one more application here, called projectile motion. You guys have seen this multiple levels of your math career. I know, like in the past, you do it in high school math, you do it in pre-calculus, you do it practically in every math class up through this one. Okay, so how that works is we have this equation. This is now dealing with vectors, so that's why we're looking at it again. And they give us all this information. We just have to label what everything is. So the initial velocity, that's not a vector, it's just a number, so we don't need the vector sign. Initial velocity is 1,500 feet per second. The alpha, the angle they gave us, which is 60 degrees, that's pi over 3. H, which is the height, it's 300 feet. And then gravity, we're going to just use our typical 32 feet per second squared because it's accelerating down. All right, so we are going to answer a series of questions just to sum up some review. You guys have done problems like this several times. Let's talk about how to do it with vectors. Here is how our vector would look. So I have that vector symbol at the top. That shouldn't have this top here. You guys can scratch that out if you'd like. It doesn't hurt anything, I guess, because it does come from a vector, but it's not a vector. So that's a 1,500, and then it's times cosine of pi over 3. So cosine of pi over 3 is going to be, so we're thinking that's our tall triangle, thinking cosine, that's 1/2. It's a small side, so 1/2 I plus, that's the I component, okay, H is 300 plus, okay, now we're going to do 1,500 times sine of that. Well, that's this other side, that was radical 3 over 2 times 1,500, or we won't do that yet, radical 3 over 2, that's times t minus 1/2 times 32 times t squared. That whole thing is j. So let's simplify a bit so it's easier to see. Okay, we get 750i plus, okay, and we have, okay, 300 plus 750 radical 3 times t minus 16 t squared j. All right, we have two portions of this. We have this, and we have that. All right, one's an x portion, one is a y. All right, so x is 750 t. We dropped our t right here. There should be a t there. 750 t range. Okay, so what that means by range is this is actually like how far it's going to go given some time. Right, so the right side will tell you how tall it actually goes. That looks on the right side more like functions that we have seen in pre-calc. So this is y being 300 plus 750 rad 3 times t minus 16t squared. This is our height. All right, I have a series of questions I want to answer that are most common for this, that'll fit a lot of different types of problems that I may ask. Will the paintball, we're done with the paintball gun. hit the ground. Right? Classic question. So we just take the y and if I want to know when it's going to hit the ground, I set this thing, sorry about that, set this thing equal to 0 and then solve for t. That's it, right? That's when we're used to doing that. We've done that probably so much in our lives at this point. If I want to know the max range, like given different t's, what is the max range? All I have to do is I just have to plug t naught in, and that'll be the time I want. If I want to know that over a certain amount of time, this is how far it's going to go, I would just plug it in. Right? If I wanted a max height, I would take y, take the derivative, set it equal to 0, and solve for t. Just like in Calc 1. Nothing changes. We're just going to have, like we just have to distill it from the components. That's all it was. Where, I hope you understand the X term. I just realized I maybe have not talked about it too much. What this is saying is this is how much X is, because remember we're dealing with an XY, right? Dealing with a vector. That tells me how many X's go by with T. Meaning, like, if 5t go by, I plug in 5, and 5 times 750 would tell me what x I'm at. So if I wanted the range of that, that's why we would just plug this in. Just we'd plug in whatever t we're on. Or maybe it would be better to say the max range would be how far it goes out. So t naught could be where... T naught probably, it would be where it ends, or B, I guess, if it's B to A, something like that. If the max range, we just plug in that last value. Right, we have one more thing here. We did max height. One more classic question they ask for impact velocity. So how fast is it going when it hits the ground? Well, I would find T naught. That's when it hits the ground, right? After it hits that, or right here, this would be, we call this T naught. There we go, that's probably better. That makes more sense, right? This T naught comes from that T naught. This T naught's when it hits the ground, so this would be the max range of when it hits. So T naught down here, we plug in T naught into velocity, because that's when it hits the ground. That's just my first derivative as a reminder. And I would have my velocity. I would have how fast it's going when it hit the ground, because that's what this says up here, right? T naught is when it hit the ground. So that's how we'd find all those. I hope that makes sense for you. It's not any different than the classic problems. It's not any different than the problems that I give in my Calc 1 class, except for the only thing that's different is they are made with T's, right, instead of X's. But we have a way to get around that with this. We just think about it differently. So same type of applications. Thankfully, calculus is done the same way on these vector value functions. It's going to be much appreciated moving into the next chapter, which will not work that way.